Questions about anything from last time? The last time at the end I promised to show you some things about the relationship between Green's theorem and various famous theorems, like the divergence theorem, and also I wanted to show you various reasons why Green's theorem is so important in the subject of harmonic functions. Green made a lot of discoveries about solving the Dirichlet problem and using he invented a thing that are now called Green's functions to solve the Dirichlet problem in more general domains than just a disk. The starting point was to understand it for the disk. Anyway, there's Green's theorem at the top. I don't have to remember Green's theorem. That's why I screwed up so much, because one thing I do remember is Stokes' theorem. And this is a differential, call that thing a differential one form. So this is Stokes. Call that a differential one form. Then this thing right here is dW. In the sense of differential forms. So let's see, how do you calculate? That would be the total differential of dP wedge dx plus the total differential dq wedge dy. And let's see, the total differential of dP would be, for example, dP would be dP dx plus dP dy. That's the total differential. And so when you wedge that with dx and use the fact that dx wedge dx is 0 and dy wedge dx is minus dx wedge dy, yeah, so that's going to be equal to, let's see, so the Q one is easy. When I wedge that, I would get, well, let's see, I'll do it in the order. The dP wedge dx would be minus dP dy dx wedge dy. And the dq wedge dy would be dq dx of dx wedge dy. So if you know how to compute with differential forms, which you'll probably learn in a differential geometry class someday, Green's just falls right out from Stokes. And Stokes is a beautiful, easy thing to remember because it's just integral around the outside of a differential one form is dW, which is a differential integral over d, the inside of dW, which is a differential two form. And so it's expressed in terms of the element of area. Anyway, that's some fancy differential geometry that was invented to understand things like Green's theorem. Questions about that? That's just a cultural thing for you to see. But I do want to explain carefully why the Green's theorem and the divergence theorem are basically the same theorem. And so I wrote out the divergence theorem last time, and you see that, let's see, if I've got a P and a Q, how could I make that integral over D the right thing? And when you stare at it for a second, you realize, what should I take? I should take F1 should be the Q function, and F2, it's a plus there, so I should take F2 to be minus P. And then when I do that, I realized that if I use Green's theorem, that's going to be equal to the integral around C of minus minus f2 dx plus f1 dy. And the question is that equal to that thing on the left, which is actually called the flux? So let's see. The question is, let's see. So I'm going to tell you this is the flux. This is what physicists and engineers would call the flux of that vector field. And it's equal to the integral of around C of f dot, the outward pointing normal, ds. Okay, and I'll explain why that's the flux. Let's see, by the way, if you look at that orientation there, my tangent vector is going to go like this. That's pretty crummy. There's my tangent vector. I'll call that T. And I'll make it unit normals. A unit normal, outward pointing normal, and a unit tangent vector. So as T goes around counterclockwise, and if I go to the right of the tangent vector, I'm getting the outward pointing normal vector. Okay, let's see, this angle right here is pi over 2 going in the clockwise direction. Clockwise. To the outward pointing normal. That's important when you start thinking about orientation and how it impacts these famous theorems. So let me explain why it's the flux. So y integral around, let's see, minus f2 dx plus f1 dy is the flux. Well, let's see. I need a parameterization to think about this. Let's let C be parameterized by x of t, y of t, where t is the arc length. So let's see, if that's, then t is going to go from 0 to the length of that curve. Where t is equal to arc length. Then the tangent vector is a unit vector. If it's arc length, then t is equal to x prime of t times I plus y dot of t times j. Okay, and let's see, my integral, this integral of c of minus f2 dx plus f1 dy is shorthand for integral from 0 to L of minus f2 of x of t, y of t, dx is x dot of t dt. And now the f1 is f1 of x of t, y of t, times dy, that stands for y dot t dt. I'll put the dt at the end. dt for both of them. That's a dot. Let's see, if I think about that, that's a dot product. Okay, so that is, what is it? It's the integral from 0 to L of, let's see, minus, let's see, I'll do it. I want to dot a vector. I'm going to dot f1 comma f2, and that's dotted with the vector minus, oh, so it's a plus, f1 times plus y prime of t and minus x prime of t dt. And I claim that this is the normal vector. And it's pointing in the right direction. Unit normal vector. I claim. That that's equal to the unit normal vector. Okay, well, it's easy to see that it's orthogonal to my tangent vector. So let's check this. Check. The tangent vector, t, remember was, let's see, t dot that vector. So here is x dot comma y dot. Remember, that's t. And I'm going to dot it with this new vector, y dot minus x dot. So this is the t vector, tangent vector of unit length. And this one, that's going to spit out plus something minus exactly the same thing. So that's equal to a big fat 0. So yes, this is orthogonal. So it's either an outward pointing normal or an inward pointing normal. I got to figure out which it is. So that's orthogonal. Check. It's a unit vector. Check, because t is. It has the same length as t. Unit vector. Check, because it has the same length as t. Okay, so the question is, does it point in or out? And that's the next thing I got to show you. And this, I like this because this shows you how nice, how useful complex numbers can be. So my next claim is y dot minus x dot points out. How in the heck would you see that? It's orthogonal, so it either points in or out, and it's at right angles. But how do you tell? And here's the way I like to do it. I like to use a complex number. So here's a nice way to see it. Nice way to see. Let's represent vector directions by complex numbers. Represent vectors in R2 by complex numbers. Okay, so I'm going to represent my tangent vector is going to be represented by x dot plus I y dot. And now my normal vector, if I'm going to rotate, remember I rotated my tangent vector pi over 2 in the clockwise direction? Then n vector would be represented by, let's see, if I multiply by e to the I pi over 2, let's see, if I multiply e to the alpha times r e to the I theta, I get r e to the I theta plus alpha. So that rotates that vector by angle alpha. And it rotates it what? In the counterclockwise. So this thing rotates a vector by alpha in the clockwise direction. Oh, no, see, it's counterclockwise. It's going around. And I wanted to go the other way. So, let's see, that makes it go counterclockwise. If I want it to go clockwise, I better put a negative I pi over 2 here. Then it goes the right direction. And so that would take like that. Okay, but what is e to the minus I pi over 2? It is, what is that? What? Minus I, right. If you think in the plane, e to the minus I pi over 2 points straight down and it's a unit distance away from the origin. That's the point minus I. So this is actually minus I. And my t is x dot plus I y dot. And you multiply that out and you get, let's see, I times I is minus 1, but I've got a minus I. So that's a plus y dot. And I got minus I x dot. And sure enough, that is my n. So that, yes. That's the vector I wanted to see is pointing out. This is my n, this is my outward pointing normal. So, sure enough, that is the flux of the vector field. And that shows you that the divergence theorem is the same as the Green's theorem when you really get, especially in the plane. Okay, any questions about that? Well, now I want to show you Green's identities now that they're just going to pop out. Green's first identity. It's that the integral around C of u dv dn ds is equal to the integral around the inside of the disk, or any domain, in fact, of grad u dot grad v plus u times the Laplacian of v dx dy. Here's the y. I let f, vector field, be equal to u times the gradient of v. In the divergence theorem. Yeah, partial v with respect to the normal direction. That's a normal vector of v. That's going to be grad v dot n. Okay, so let's see. Let's do it. I'll have the integral around C of f dot n ds. Okay, that would be the integral around C of u times grad v dot n. And that's the definition of the normal vector. ds. Okay. This is the directional derivative in the outward pointing normal direction. That's dv dn by definition. And this is going to be equal to the integral over d of the divergence of f. dx dy. And the divergence of f, when you calculate it, is exactly that thing right there. So this is going to be the divergence of u grad v, and you just calculate it. And sure enough, you got to check this. It's a matter of writing it out. Check. That's grad u dot grad v plus u times the Laplacian of v. It's just a matter of writing it out and checking it, sure enough. So Green's identity, that's all there is to it. Green's first identity. And once you know Green's first identity, Green's second identity pops right out. Let's see, Green's second identity is the integral around the outside of u dv dn minus v du dn ds is equal to the integral over the inside of u Laplacian v minus v Laplacian u dx dy. And actually that's very easy to get because when you subtract, it's just a matter of subtracting two Green's first identities. So remember y. Green's first identity was integral around C of u dv dn ds equals the integral around d of grad u dot grad v plus u Laplacian v dx dy. Stare at that for a minute and realize, oh, I can switch the u with the v. And when I do that, I get v du dn here when I switch. When I switch here, grad u dot grad v is the same thing. So this would be grad v dot grad u, and those two things are equal because that commutes. And this one would be plus v Laplacian u dx dy. And so the nice thing when I subtract those two things, those gradient term go away because they cancel each other. And so what I do here is I subtract, and that, sure enough, that gives me the identity because that thing cancels out. So check. Green used his second identity to prove the averaging property for harmonic functions. So here's Green used his second identity show that harmonic functions satisfy the averaging property. And that's a beautiful argument. So I thought I'd give it to you. Now that we have all these famous identities. So let's see. Harmonic means C2 smooth. Laplacian is identically 0. Okay, so let me show you how it works. Last time I showed you how you can get the Green's theorem for an annulus. So I'm going to take, the picture is going to be, I'm going to do it for a unit circle. This one I'll call C1, because it's going to be the unit circle. And I'm going to have a small circle on the inside. I'll make it go clockwise. And that's going to be called C sub epsilon, because this radius is going to be epsilon. And then the region between the two is going to be this. And that's I'll call that omega, since it's not a disk anymore. And I'm going to do this, my function u is this u is going to be the harmonic function. And v is going to be a special harmonic function, namely the natural log of the radial direction. That's harmonic. You just have to check it. So let's see, what would that be? That's harmonic. That's the, let's see, what's the log of 1 over r? That would be the natural log of the square root of x squared plus y squared. That's 1/2 the natural log of x squared plus y squared. You check. Check that the Laplacian is equal to 0. And that has just the right singularity at the origin to spit out the averaging property. And that's what Green realized. And so, in fact, that's the Green's function for the point 0. When he started thinking about these things, that's what led him to invent the Green's function. So let's see, how does it go? It's not going to be difficult at all. We've got Green's second identity, which is u times dv dn minus v times du dn ds equals, here's the great thing. By the way, when I proved Green's theorem for the annulus, I cut it up into 4 pieces where I had Green's theorem. And that's how, so that would work here just the same. Then I'd get u times Laplacian v minus v times Laplacian u. But those are both harmonic functions. Let's see. Remember the integral around c. This is the integral around the outer one, union. Let's see, the c epsilon is going around. I'll make that one go clockwise, like I have in the picture there. Okay. U is harmonic, so this is 0. And v is harmonic, so this is 0. So the right-hand side is the big fat 0. All right. And this integral is going to be the integral of C outer yeah, so I have the integral around the outer one, dv dn, minus v du dn ds. And now I can put it on the other side, that's equal to integral around c sub, if I go the other way, that would make that integral minus. That would make it counterclockwise. That c sub epsilon is clockwise. When I put it going the other way, it's going to be counterclockwise. And so I get the same thing here. And these integrals turn out to be very simple to compute. Let's think about it. Let's see, remember v is equal to 1 over r. I'm sorry, log of r. And so if I differentiate with respect to the normal direction, that's the r direction. dv dn is equal to 1 over r, with r equal 1. So that's equal to that's equal to 1. So that first thing is the average is going to be the average of u, basically. All right. And v is the log of r is equal to 0 on the boundary. Equals 0 on C1. Okay, so that makes that thing very simple. This is the integral around the circle, a big circle of radius 1 of u ds. That's spitting out the average. Or it's actually, let's see, there's going to be a 2 pi coming in somewhere. If I had 1 over 2 pi there, that would be the average. The 2 pi is going to come on the other side here when I mess around with this other side. So that's going to be equal to, what does this side do? Let's see, dv dn is 1 over, remember it's 1 over r, and on this curve, that's going to be 1 over epsilon. That's kind of scary to go 1 over epsilon. Yeah, so that first one, this first one is going to be minus the integral along minus c sub epsilon of 1 over epsilon times u ds. All right, and as that epsilon goes to 0, that's just the integral of a constant. So let me think about what that is for a second. The second one is going to be minus and minus. That'll be plus the integral. This one is plus the integral along minus c sub epsilon of log epsilon. That's kind of scary. Times something that's bounded. Du dn, whatever it is a bounded function. Times ds. Okay, so let's call this, let's think about that first integral. That's going to be equal to minus, let me calculate that integral. Integral from 0 to 2 pi u epsilon e to the it. 1 over epsilon sits there, and the element of arc length is going to be epsilon dt. The great thing is that epsilon cancel, 1 over epsilon gets canceled by the epsilon dt. And this one is going to tend to minus, I'm going clockwise, I'm sorry, minus that, it's going to be plus, I put it on the other side. I'm sorry, in my notes, there's no minus here. When I put it on the other side, it stays the same. Oh, I see. What? Right, so there's no minus here. That's where I screwed this up. Minus. Sorry about that. There's no minus here. That's going to go to 2 pi is the length times u at 0. And that's the averaging property. So I claim that this last thing is going to go to 0 plus something that tends to 0 as epsilon goes to 0. Okay, and that's, let's see, think about that. Du dn is a normal derivative of u going around a circle that's really small. And that would be a bounded thing. So this du dn is a bounded thing, and all those directional derivatives would be bounded as you go around that little circle. Remember, when you take directional derivatives, you're differentiating in a unit normal direction. So whatever those are, they're bounded. Let's say it's bounded and less than m. Okay, so to show that that last something goes to 0, I have to, let's see, I have a integral of natural log of epsilon times something bounded times ds. That would be less than or equal to log of epsilon comes out, the bound comes out, times the length of the curve. Length of c minus epsilon, which is 2 pi epsilon. Then you see something from freshman calculus you remember, hopefully. Epsilon log epsilon goes to 0 because epsilon dies away much faster than log epsilon blows up. So the aha moment is L'Hopital's shows epsilon times log epsilon goes to 0 as epsilon goes to 0. Remember how you do it? Epsilon times log epsilon is log epsilon over 1 over epsilon. Then you use L'Hopital's rule. And so it's easy to estimate that second thing there. That goes to 0. And so it all boils down to the estimating the first thing, and that's a very straightforward calculation to see that it tends to the value of u at 0 times 2 pi. And that's just by continuity. You only need u to be continuous to deduce that. Okay, I thought it was important to see that, to sort of dot the last I in this discussion. Questions about it? It's technical, but it's the kind of math that if you really want to understand these things at a deep level, you got to sit through. And it's kind of math you have to sit through and check and recheck to make sure you believe it. So finally, after we let epsilon go to 0, we get that the integral around the outside of u ds equals 2 pi times the value at 0. And that's the averaging property. I proved it for the unit disk, but of course it works for any disk. Once you know it for the unit disk, you can scale it and see it for any disk. Okay, so you might ask why I did this. Did we really need this? There's a philosophical reason why this had to be done. So what did I show? Answer is yes. I showed the Poisson integral formula solved the Dirichlet problem. And I let you get excited about that. And then I showed you that the solution to the Dirichlet problem satisfies the averaging property. And the averaging property implies the maximum principle. And the maximum principle implies uniqueness. Okay? So I showed the Poisson integral solves the Dirichlet problem. I saw the Poisson solution satisfies the averaging property. So the Poisson integral is equal to the averaging property is equal to the av on the circle at 0. But I didn't show that harmonic functions satisfy the averaging property. And I needed that to show uniqueness. So the hang-up I need to know general harmonic function satisfies the averaging property, so I can use the maximum principle to show uniqueness of the solution to the Dirichlet problem. So I need to know general harmonic functions, not just the ones that come from the Dirichlet integral. Satisfy the averaging property to be able to show uniqueness. So that's a philosophical question. I found a solution to the Dirichlet problem. The question is it the solution? Show uniqueness of the solution to the Dirichlet problem via the maximum principle. Which follows from the averaging property. So I would have to show it. to complete this circle of ideas. Okay, so I'm not wasting your time with something historical. To complete the subject, I really have to do it. Anyway, I think it's worth seeing because it's the kind of thing you might see again, especially if you take advanced physics classes, and comes up in electricity and magnetism in lots of places. Questions about it? I'm not going to test you about this stuff, but I thought you ought to see it. Well, fortunately, I'm running out of time because it's tiring to do that, something that technical, but it's worth the effort, I think. The next question I want to address in here is something back down to earth about Fourier series. Something I told you that Fourier series, what they do at jumps. And the question I want to explain now is why. And this turns out to be surprisingly elementary and easy. Why do Fourier series converge to the midpoint of jumps? It turns out that if you understand it for one simple one, you understand it for all of them. The fact is, if you understand the test case, then you understand all jumps. Understanding a model case is all you need to do. So the model case I'm going to understand is the very simple jump. We've seen it. I've been graphing it and playing around with it. It's going to be +1 to the right and -1 to the left. And let's see, this is minus pi, and this is plus pi. That's an odd function. So when you write out the Fourier series for it, all the cosine terms are 0. And the average is equal to 0. So A naught is the average, and that's equal to 0. And of course, the sine functions are all 0 at 0. So the Fourier series is going to be a big fat 0 at 0. And you know, I graphed it using a maple and showed you that the Fourier series kind of looks like it's 0 at pi, minus pi also, and then it comes out and overshoots by Gibbs phenomenon, and then kind of gets sucked in close for a while, and it overshoots again. And so it looks like that. Kind of. And so that I didn't have to really think hardly at all about that. I know that an odd function, all the cosine terms are 0. A naught is one of the terms that's 0 because it's average. And so all the bn's, who cares what they are, all signs vanish at x equals 0. And so the Fourier series is going to be 0 there.